transmission lines, line profiles, series on transmission line theory, lecture number 1.30. Transmission lines are widely used conductive media to transfer low frequency telecom signals from one point to another point. When a source is connected to a line, the signal starts traveling from source end to load end in the form of a wave. This wave is called forward wave. When forward wave falls over the load impedance, partly it goes into the load, with the remaining getting reflected back towards the source. This reflected one also travels in the form of a wave. It is called reflected wave or reverse wave. Now over the line there are two waves, forward wave and reverse wave. Interference takes place between them, resulting in standing wave pattern. All these waves, forward wave, reverse wave, standing wave too, they are associated with voltages, currents and also impedances. The voltage and current over the line, they are governed by certain equations. These are in two sets. First set is called Telegrapher's line equations or transmission line equations. These are first order equations. Second set is called wave equations. These are second order differential equations. If we need to have an expression for voltage and current at an arbitrary point over the line, we can have those expressions by solving wave equations. First, they give general solution, and by applying boundary conditions or initial conditions, one can obtain particular solutions, specific solutions for voltage and current at an arbitrary point over the line. In the present session, the focus is on derivation of transmission line equations, wave equations, and how to obtain current and voltage expressions from the wave equations. The electrical behavior of the line when a source is connected is described by a set of partial differential equations. These equations are known as transmission line equations. Another name is Telegrapher's equations. These are two in number, and as already mentioned, they are first order partial differential equations governing the profiles, that is variation of voltage and current over the line as function of time and position x. Here are shown the two equations. Notice these are partial differential equations. These are in time domain. These two equations, they connect voltage and current. These equations involve R, L, G and C. These are primary constants of the line. In the first equation, voltage gradient, dou V by dou X, voltage gradient is given in terms of current, Ix of t, dou Ix of t by dou t. Current is there on the right hand side. In the second equation, current gradient, dou I by dou X, it is given expressed in terms of voltage. These equations, they are for a line that is lying along x-axis. Here is shown the line. It is lying along x-axis. Length of the line is L. We consider an arbitrary point P over the line. This point is at a distance of x. From source end descending end, it is at a distance of D from load end. At this point, let us suppose voltage is V, current is I. V is V x of t, I x of t. Now we consider a small length, differential length delta x at point P. At x plus delta x, let us suppose voltage V is V x plus delta x t, I x plus delta x t. At P it is VI, VXT, IXT. At x plus delta x, voltage and currents are Vx plus delta xt, Ix plus delta x t. Now, this small length of line, it is replaced by its equivalent. The equivalent is shown here. This is current I, at the other end current I, x plus delta xt, and resistance R delta x, L delta x. This is equivalent circuit. G delta x, this is C delta x, this one. So this is equivalent circuit of this differential length line. With respect to this equivalent circuit of differential length line, those equations are valid or derived. To derive them, consider a differential length delta x of a line and using lumped element model, its equivalent circuit can be written. It is already shown. Let us suppose the quantities Vxt and Ixt denote instantaneous voltage and current at the left end of the differential section, and Vx plus delta xt, it is equal to V plus delta V, and Ix plus delta xt equal to I plus delta I, denote same quantities at the other end. Application of Kirchhoff's voltage law at the node gives Vxt minus R delta x, Ixt minus L delta x, dou Ixt by dou t minus Vx plus delta x t equal to 0. Kirchhoff's voltage law. Similarly, application of Kirchhoff's current law at the node gives Ix of t G minus G delta x V x plus delta xt minus C delta x dou V by dou t at x plus delta xt minus I x plus delta xt equal to 0. Now, these two equations, these are basic equations. They can be modified. They can be manipulated by writing this quantity Vx plus delta xt by V plus delta V, I x plus delta x t by I plus delta V, and then dividing the entire equation by delta x, one can obtain those two equations. Now, those two equations, as already mentioned, they are called line equations. Those line equations, they involve R and G2, which we have derived. But when the line is lossless, R disappears, G also disappears. Ultimately, we are left with two terms, one on the left hand side, one on the right hand side. Minus dou V by dou x is equal to L dou I by dou t. This is voltage gradient, whereas this one is right hand side, L multiplied by rate of current change. Similarly, second equation, minus dou I by dou x, this is current gradient, right hand side it is C dou V by dou t, rate of voltage change. So these are line equations, basically the equations that are given earlier with R equal to 0 and Z equal to 0. Now, manipulating these two equations, by applying dou by dou x to first equation, one can obtain first wave equation. Dou square V by dou x square equal to LC dou V square by dou t square x of t. Similarly, applying differentiation with respect to x to the second equation, this equation, and then combining it with the first equation, second equation can be obtained. Now, line equations, one can notice these are first order equations, whereas wave equations are second order equations. And also note, line equations connect voltages with currents or current with voltage at a particular point. Whereas wave equations, they involve both sides, only voltage. Left side voltage, right side also voltage. Left side current, right side also current. Phasor domain. The equations that are shown in the previous slide, they are in time domain. Time is there. You can see time is visible explicitly in those equations. So they are time domain equations. Those equations can be converted into phasor domain by replacing dou by dou t with j omega. Now in phasor domain, line equations, they appear dv by dx equal to minus zv, di by dx equal to minus yv. Notice in phasor domain equations, it is not partial differentiation, it is ordinary differentiation. That is one aspect. Another aspect is voltages and currents are not instantaneous or time varying voltages and currents. They are phasors. They are complex quantities. That's why they are being shown with boldface letters. Here Z, in the first equation, Z is there. Z means R plus Z indicates R plus J omega L. Second equation involves Y. Y here means G plus J omega C. Second set, d square V by dx square equal to gamma square V, d square I by dx square equal to gamma square I. This is second set. This set is the wave equation in phasor domain. First set is telegrapher's line equations or transmission line equations, whereas second set is wave equations. Here gamma is there. Gamma means propagation constant. The wave equations, one can notice, are second order ordinary differential equations in phasor form. Their solutions involve four arbitrary constants. There are two equations, second order equations. So each equation, solution of each equation involves two arbitrary constants. Four solutions, four arbitrary constants exists in the solution of the two equations. These constants are usually complex. Out of four, only two are independent, and hence both the voltage and currents can be expressed in terms of these two independent constants. Line voltage and currents. First equation, if you consider first equation, V is V plus some constant, arbitrary constant, e power minus root zyx plus V minus e power root zyx. This is the general solution involving arbitrary constants, two arbitrary constants, V plus V minus. Now here one aspect is to be mentioned. Already told, Z means R plus J omega L, Y means G plus J omega C. In the solution, we come across the product ZY under square root. Here we are going to see this product under square root is equal to gamma, that is propagation constant. Propagation constant is an important parameter capable of giving the transmission line properties of a line. So by replacing root Z by Y by gamma, we have this equation. Similarly, I is I plus e power root zyx plus I minus e power root zyx. Of course, this can be put in this form. But V and I, these two are related through telegrapher's line equations. Taking the help of telegrapher's line equation, I can be expressed in terms of V plus and V minus, like I equal to minus Y naught minus V plus e power minus gamma x plus V minus e power gamma x. It can be reformatted in this way. So now at the end, we have two equations, one for V, one for I. V is in terms of V plus V minus. I2 is in terms of V plus and V minus. So V and I now are available in terms of two arbitrary constants, V plus V minus, of course, which can be, we are going to see, these are arbitrary constants. These can be evaluated in terms of sending end voltage or current and impedance, or receiving end voltage or current and impedance. Note, there exists in general two waves over the line traveling in opposite directions. The expressions involves two exponentials. A term involving e power minus gamma x, actually representing plus x traveling wave called forward wave, and another term involving e power gamma x denoting minus x traveling wave called reverse wave. In the expression for V and also for I, one can notice there are two terms. One term involves e power minus gamma x, another term involves e power gamma x. But e power minus gamma x is the equation of a wave traveling in positive x direction. So because of the presence of those expressions, one can say that waves, forward wave, reverse wave, exist over the line. The first term in the expressions denote voltage and current in the forward wave, whereas second term represents those pertaining to reverse wave. Interference takes place resulting in standing wave pattern. The ratio of voltage to current, this is an important aspect one has to keep in mind. In case of incident wave, it is Z0, characteristic impedance of the line, but it is minus Z0 in case of reflected wave. Before going further, just to remind you, Z0 characteristic impedance is square root of Z by Y, and propagation constant, as already mentioned, it is zy. If you multiply z with y under square root, it is propagation constant. If you divide z by y under square root, it is characteristic impedance of the line. It is plus z naught in case of incident wave, forward wave, minus z naught in case of reflected wave. The vector ratio v to I at any point over the line gives line impedance. At that point, if the point under consideration is right over the load, the ratio becomes equal to load impedance. Consider a line. Here certain voltage exists, certain current exists. Voltage to current ratio is line impedance by definition. If this point happens to be here, then the line impedance becomes load impedance. When the line is lossless, note alpha is 0. Both the waves, incident and reflected wave, can be found traveling with constant amplitude. However, when alpha is not 0, line is lossy. See, alpha 0 implies R equal to 0, G equal to 0. Alpha not equal to 0 means either R or G or both are not zeros. So attenuation is there, the line is called lossy, and the waves can be found traveling with a decreasing amplitude. When the line is lossless, terminated over pure resistance, a maximum or minimum of standing wave pattern exists right over the termination. What he is trying to tell is, suppose here is a lossless line, termination is some resistance. Now standing wave pattern exists over the line. In general, standing wave pattern means maximum, minima, etc. etc. When the termination is pure resistance and the line is lossless, when these two conditions are satisfied, then exactly over the load that exists either maximum of the standing wave pattern or minimum of the standing wave pattern. Arbitrary constants need to be evaluated, and it requires, here arbitrary constant means V plus V minus. What we have as expressions for voltage and current at the point P, those expressions involve constants. They are to be evaluated. Then only we will get specific particular required expression for voltages and currents. Arbitrary constants need to be evaluated and requires initial or boundary conditions. Here number of arbitrary constants are 2, and hence number of conditions required is also 2. Initial conditions usually are sending end or receiving end voltages, currents and impedances. Any two will do. Let us now evaluate arbitrary constants in terms of sending end conditions. Sending end voltage, sending end current, sending end impedance. Let us suppose the initial conditions given are sending end voltage and currents. It is required to evaluate the arbitrary constant V plus V minus in terms of these quantities. See, idea is this. Here is the line, sending end voltage, sending end current is given. A point is there at a distance of X from the sending end. Sending end voltage usually indicated by Vs, sending end current is indicated by Is. At point P, V. What is V? What is I? In terms of Vs and Is. This is what we are going to do right now. It is required to evaluate arbitrary constants V plus and V minus in terms of these quantities. By definition, the sending end voltage and current are Vs equal to V at x equal to 0, Is equal to I at x equal to 0. Now it results Vs equal to V plus V minus. How this thing has come? We know V. V is V plus e power minus gamma x plus V minus e power gamma x. These are the equations which we had from wave equations. Now Vs is V at x equal to 0. So when x equal to 0 is considered, it becomes V plus V minus. Similarly, Is can be found equal to V plus minus V minus by Z naught. From this, Is Z naught equal to V plus minus V minus. Respectively, solving these relations, the arbitrary constants can be obtained. Now you have two relations. This is one relation, this is another relation. Solve them to find V plus V minus. These two equations are in terms of V plus V minus. Solve them. V plus is half Vs plus Is Z naught. V minus is half Vs minus Is Z naught. Substituting those things in the general expression for V, we have ultimate with a little bit of manipulation. V is Vs cos h gamma x minus Is Z naught sin h gamma x. Similarly, an expression for current can also be obtained. Same way, like the way we obtained expression for voltage, current also can be obtained. The voltage and current can also be expressed in terms of sending end current and impedance. Instead of sending end voltage, you can consider sending end impedance and express the voltage. V is half Is Zs plus Z0 e power minus gamma S, gamma x plus Zs minus Z0 e power gamma x. Of course, a little bit of manipulation gives us this expression. I think these are repeated. Half Ix Zs plus Z0 e power minus Zs minus Z0. It is repeated. I think there is no need. The second one. Similarly, for current, it can be found. It is equal to I equal to half Is Z Y0 Zs plus Z0 e power minus gamma x minus Zs minus Z0. This is for current. Now, receiving end conditions. How to express general expression for voltage and current in terms of receiving end conditions? First, we consider receiving end voltage and current. VR, receiving end voltage and current, VR is V at x equal to L. IR equal to IR equal to I at x equal to L. This is the line. This is the point P. Length of the line is L. So this is the receiving end. At the receiving end, what is X? X is equal to L. So here voltage, here current. Current and voltage you can obtain by considering X equal to L. Okay. It results in VR equal to one equation, IR equal to another equation. Now solving this, we get V plus half VR plus IR Z0 e power gamma L, V minus equal to half VR minus IR Z0 e power minus gamma L. So substituting in the expression over voltage, we get VR cos H gamma D plus IR Z0 sin H gamma D. Note that L minus X equal to D. Similarly, for current, it can be obtained IR cos H gamma D plus VR Y0 sin H gamma D. Here Y0 is 1 minus Z0. Z0 is characteristic impedance of the line. The voltage and current can also be expressed in terms of receiving end current and impedance using VR equal to IR ZR. See, in the previous expressions, VR is there, IR is also there. So you replace VR by IR ZR. With replacing and a little bit of manipulation gives V equal to half IR ZR plus Z0 e power gamma D. Actually, this is forward wave. ZR minus Z0 e power minus gamma D. This is reverse wave. Similarly, for current, it can be written as half IR Y0 ZR plus Z0 e power gamma D minus ZR minus Z0 e power minus gamma D. This is forward wave. This is reverse wave. Note that here D is there. With all the substitutions and manipulations, we get voltage and current in terms of sending end current and impedances as like this. This is forward wave, this is reverse wave. With the receiving end current and impedances, we will be getting like this. This is forward wave, this is reverse wave. Here it is in terms of X, whereas this is in terms of D. X is distance of the point from sending end, whereas D is distance of the point from the receiving end. In terms of sending end voltage and currents, this is the expression. Hyperbolic functions are there. In terms of receiving end voltages and currents, this is the expression. This is also in terms of hyperbolic functions. These are some of the things which I like to share with you. Here mainly what we did is the voltage and current at a point over the line, they cannot assume arbitrary values. They are governed by equations, Telegrapher's equations and wave equations. An expression for voltage and current profiles over the line can be obtained. It is obtained in the present session. And